Welcome to topic 9, in which we're going to move on to look at vibration absorption spectroscopy and Raman vibration spectroscopy. As with rotation, sometimes it's useful to have a classical picture of what's going on in spectroscopy. So if you think about vibrations classically, you have the view of a diatomic molecule as being two atoms of certain mass held together by a spring. This spring has a certain stiffness, a certain force constant, and an equilibrium length. So we can draw a molecule something like this. So we have a mass 1 atom, got a spring, and then another atom of mass m2. This spring has a force constant K and an equilibrium length Re. If you now stretch or compress this molecule, the spring creates a restoring force which is proportional to the magnitude of the displacement. So we can write this expression here. So where the force is equal to minus K, where K is the force constant, multiplied by R minus Re, where Re is the equilibrium bond length of the molecule. The potential energy of a spring is then given by this expression here. So we've seen K is the force constant, Re is the equilibrium bond length. This is actually the equation of a parabola and describes a so-called harmonic oscillator. So a harmonic oscillator potential looks like this. So we have potential energy up the left, we have bond length on the x-axis, and we have this curve. This is how a spring behaves. And if you have a spring with a reduced mass of mu and a force constant K, so here we have mu, here we have K, then the vibrational frequency of this spring is given by nu, the Greek letter nu. So if you know the force constant, you know the reduced mass, you can work out what the natural vibrational frequency is. The harmonic approximation is only an approximation though, so real molecules are better described by a Morse curve. So here we have a plot where the harmonic potential is in pink and the Morse curve is in grey. And you can see that the harmonic model is okay around the bottom of the well. So if we're down here, the harmonic model is quite good. But if we go up to higher energy, so here, we can see that the harmonic model is actually not very good. We'll see a correction factor for this later on. So we've thought a bit about the vibrations of a spring. How does a vibrating molecule interact with light? So here's a classical picture of what's going on in vibrational spectroscopy. If we can imagine a linear triatomic such as CO2, this has a delta plus and a delta minus. And if you think about the asymmetric stretch, so as one bond gets longer, the other bond gets shorter. So it looks something like this. We can now think about the dipole moment of this molecule. So initially there's no dipole moment, but then it gets bigger and points in one direction, and then it gets bigger and points in the other direction. If we were to plot this on a graph as a function of time, we get a nice curve. And in the same way as when we were looking at rotations, if we've got an oscillating dipole, this will then interact with the oscillating electric field of light. So this is how vibrational spectroscopy works. You'll have to remember this is just a classical picture, so it doesn't give us all the details we need, but it helps us get a feel for what's actually going on. Of course, to understand what's going on, we need to go to quantum mechanics. So we can solve the Schrödinger equation for a simple harmonic oscillator, and this leads to the introduction of a vibrational quantum number, V, and the existence of discrete energy levels. So if we have our harmonic potential, it looks something like this. We'll now get energy levels with different V. So this is V equals 0, this is V equals 1, V equals 2, V equals 3, V equals 4, and so on. the energy in joules of one of these vibrational states is given by this expression here. Here we've got h, so Planck's constant, nu, the vibrational frequency, and we've got v, the quantum number. You can see we've got to be very careful to distinguish between nus and v's. So first of all, you need to get them clear in your mind what they mean, and then make sure that when you write them, you're also very clear. We can express this in terms of a vibration wave number, nu tilde, and that gives us this expression here for the energy of these states. One of the very interesting things that happens when you solve the Schrödinger equation for a simple harmonic oscillator is you get so-called zero-point energy. And zero-point energy, often abbreviated to ZPE, is this energy gap here. The interesting thing here is that the lowest possible vibrational state doesn't have zero energy. It's got a finite non-zero energy. And this is described by the zero-point energy. This is a purely quantum mechanical effect, and it doesn't happen in a classical case. Okay, so we've understood a little bit about what's going on, how light interacts with a vibrating molecule, and how solving the Schrödinger equation gives rise to vibrational energy levels. We now need to think about the selection rules, which account for transitions between these energy levels. As always, we've got a global rule and a specific rule. Here, the global rule is that there must be a change in the electric dipole of the molecule during the vibration. So an example could be a linear molecule like CO2. If it bends one way, then the dipole moment will point one direction, and if it bends the other way, then the dipole moment will point in the other direction. So this is a case where this happens. The specific rule for vibration absorption spectroscopy is delta V equals plus or minus 1. So this says that V, the vibrational quantum number, can change by plus or minus 1 in a transition. We can also work in terms of vibrational terms, and this is working with units of centimetres to the minus 1, working in wave numbers rather than joules. So the wave number of a specific level can be written as the vibrational term g of v, and this has units of centimetres to the minus 1. So we get a vibration wave number from an energy in joules by dividing by hc. So if you remember the expressions from a couple of slides back, we can now write g of v equals nu tilde multiplied by v plus a half in this expression here. We know from the selection rules that an allowed transition is delta v is plus or minus 1. So we can get the wave number of a transition, so a transition wave number of allowed transition is therefore just equal to nu tilde. So it's a very simple expression. Let's think about vibrational transitions and how many peaks we'd expect to get in a spectrum. If you think about a CH bond, they come at around 3000 centimetres to the minus 1 in an infrared spectrum. And 3000 centimetres to the minus 1 is much larger than KT at room temperature. Remember right back to the beginning of this course when we were thinking about KT at different temperatures as being a rule of thumb for how much energy is available. This means that at room temperature, most transitions will start from the ground vibrational state, so the state V equals 0. So therefore, in a spectrum, the transition from V equals 0 to V equals 1 is going to be the main transition, and this is termed the fundamental transition. It is possible to have transitions from higher initial values of V, so if, for example, if you went from V equals 1 to V equals 2, but these are called hot bands. They're called hot bands because in order to have enough population in the state V equals 1, often you need to heat the molecule up. we'll do some calculations on this in the workshops. Okay, so we've talked about vibration absorption spectroscopy. Well, you can also have Raman vibrational spectroscopy. So instead of having the absorption of light, we're getting scattering of light. So again, we've got our selection rules. So the global selection rule for Raman vibrational spectroscopy is that there must be a change in the molecular polarizability of the molecule during the vibration. The specific rule, as with the vibration absorption spectroscopy, is that delta V is equal to plus or minus 1. You can see that the global selection rule is different for Raman vibrational spectroscopy to that for vibration absorption spectroscopy. And because of this difference, often infrared and Raman vibrational spectroscopies are complementary. So sometimes you will see a peak in the Raman spectrum, which you won't see in the absorption spectrum, and vice versa. Okay, some homework for you now. Some pages in Housecroft and Constable to have a read through, and some worked examples to have a go at. And that brings us to the end of topic 9.